Next on the agenda here, Nader Sehatbakhsh, assistant professor in the electrical and computer engineering department at UCLA. His interests are hardware security, computer architecture, and security and privacy in IoT systems. Prior to joining UCLA, he received his PhD from Georgia Tech, working on mitigating side channel leakages in computing systems. His work has been recognized with several awards and honors, including the Micro 49 Best Paper Award. Nader, go ahead.
So thanks, Jeff, for the introduction, and thanks everybody for joining in. So today, as the title suggests, I want to talk about the challenges in supply chain, in securing the supply chain, essentially in future systems, mainly the advanced heterogeneous integration that we are experiencing these days. So let me start with the story of Big Hack, which also was slightly covered in previous speaker's talk. So a few years ago, Bloomberg actually published this very interesting article that they showed that a large number of motherboards are actually being compromised by adding this very tiny piece of hardware that's been added to this motherboards. And according to the article, these motherboards actually ended up being installed in many of these servers and very critical systems. So FYI, the article itself, the accuracy of the article is being challenged, but generally what the article claimed was that many of these systems, including AWS servers, Apple devices, many of the national labs, so on and so forth, has been compromised by this tiny chip that's been added to the motherboard. And then according to the article and some other similar articles, this was just not, the single incident that happens. There were actually quite a few of these things that happens in the past decade or so. And as I said at the beginning, the accuracy of some of these claims were not confirmed. But technically, all of these, if you're looking at them in technical perspective, all of them are technically possible. So the question is that we never know that whether these are actually happen or not. So the moral of the story that I wanted to tell is essentially the security of the global technology supply chain has been compromised, and whether these stories are true or not, it's very possible that as we are speaking, there are new Harvard Trojan being introduced in our systems. So the main problem of these outsourcing, unfortunately, is getting worse and worse, because mainly if you look at the U.S. global chip production market share, we are reducing from 37% in 1990s to only 18% right now. So we are actually having a less and less number of chips being manufactured locally in the United States. And then the unfortunately the outcome of this outsourcing and sending the chips and being manufactured outside is essentially this concept of Harvard Trojans. So the Harvard Trojan are these malicious modifications in hardware that, as the picture I'm borrowing here from my colleague, can be introduced either at the design level. So we have these third-party IP cores that a malicious designer can actually introduce some backdoors or some modifications at the design level, or even if the designer can be trusted, the fabrication foundry or company can actually introduce these modifications during the manufacture. So the main question is, okay, in light of these challenges, where we are headed? Are we fixing this problem, or are we making it worse? And unfortunately, the answer is the latter. The main reason for that is that we are building even more complex systems, and not only that, we are actually making complex SoCs and heterogeneous systems. For example, many of you probably know the new design for Apple M1, which essentially what it does is that even integrating more things on a single piece of chip. So now that before, for example, we were given with a relatively less complex motherboard, nowadays we are having lots of different chips and units in the same piece of silicon. So the more important consideration is that we are shifting the paradigm of the computation, and we are essentially moving to a more heterogeneous systems. Many of you probably have heard about the concept of chiplets and wafer scale computing. So essentially, the idea is that given this advancement in manufacturing and integration, we can actually completely replace the PCB design and replace it with the silicon die that we can just directly bond and integrate different chips onto the same die, same silicon, and then these can give us a massively parallel and very efficient in terms of both performance and power consumption. And then we can deeply integrate and integrate the memory and the chips and the logic together. So in this scenario, we are facing with even more challenges. So to understand this, we are facing with two major problems in this future's technologies. The first one is what I formulate and call it as known unknowns, which is essentially we cannot trust each individual chips. So this is kind of like what we have seen before in Harvard Trojan detection. That's essentially if the chip is being manufactured has been outsourced or being manufactured by a third-party IP and so on, we cannot trust it. But even more interesting is that we are facing also with a problem that I call unknown unknowns, which is essentially similar to the big hack story that I tell. We may not even know that what we should exactly look for, right? So we can face with this challenge that in some cases we are having this issue that, for example, a tiny chip can be added to our system, or like a specific chip can be repurposed, or some backdoor can be added to the system. So not only we have to use our traditional systems to detect these Harvard Trojans, we also need to come up with new techniques in order to detect this new type of unknown challenges. So before I go forward, is there any question, Jeff, that I can answer? Or should I continue?
Continue, nothing has come up yet here.
All right. So given these challenges, the question really is that what we can do, right? So what are our solutions, and what are the new things that we can do? And the answer to this question, the first answer is that we need to kind of define our trust model, right? So we need to define whether we can trust the foundry, we can trust the designer, we cannot trust either of them or both of them, and so on. Right, so any solutions that we come up with has to have this trust model in it. Another important consideration is that we need to understand what we have, right? So for example, in many of these systems, what we have is what is called a golden model. And golden model is essentially defined as this chips that is Trojan-free. So for example, we are giving a group of chips. Some of them are afflicted with the Trojans and some of them are not. And if we have the golden model, we can actually do something meaningful with it. Another consideration is that whether we are given the design files, for example, do we have the RTL files? Do we have the malware-free netlist or not, right? And then if we do have those, then again, we can come up with some solution. But if we don't, we need to search for new type of solutions. So based on these assumptions and this formulation, the state of the art and status quo for Trojan detection is essentially can be categorized in two different solutions. The first one is what I call reverse engineering or physical inspection. So the idea here is that you can actually physically inspect the device. You can remove the packaging, you can do the image processing in order to actually kind of reverse engineer the system in order to find the exact net list. And once you have that, you can kind of, for example, compare it with your original net list, and then hopefully be able to find the Harvard Trojans. The advantage of this method is that it's very effective on extracting Trojans, But unfortunately, this is destructive, and in many cases, it's very expensive because it requires sophisticated equipment. An alternative scenario and solution for this is using side channels. So side channels that I'm showing here are these physical signals that is being produced as the artifact of the computation. For example, as your devices start executing different instructions, the temperature of the device goes high or goes low. And based off that, you can kind of see a correlation between, for example, the physical characteristics and your device. For example, if you're running program A versus if you're running program B, the temperature that your processor is creating would be different, right? So what you can do is essentially using this side channels information for detecting Trojans. The fundamental idea is that given that for example, given the golden chip model, you can compare the side channel signals that you're receiving from your reference system, and then you can compare that with your potentially malicious Trojan hardware. And then if there is a significant difference between these two, you can use this in order to detect the hardware Trojans. The main advantage of this system is this is very non-destructive, and in most cases is low cost. But the main challenge in side channel analysis for hardware Trojans is that mainly you cannot detect subtle changes compared to the destructive method and the physical image. So given these different solutions, the current challenge in most of these solutions is essentially there are two challenges. The number one challenge is that in many of these systems, we're kind of relying on having a reference model. As I said before, it's called golden chip. So we are relying on this fact that we can somehow build and manufacture this chip in a reliable fashion so that we have that reference model, and then maybe we can mass product it using outsourcing, and then we can compare these two methods and then find the hardware Trojans. But the critical question is that what if the model is not available? And if going back to my original argument that we are moving toward more heterogeneous systems with chiplets and dialects, actually this is a very valid assumption, because we are given lots and lots of these small chiplets on our system, and it's not very realistic to think about that we are giving the chiplets, we are given the golden chip model. Okay.
Just to jump in with a question here,
Sure.
that came in related to this here. Does side channel analysis require a known good reference?
It does. Yes, that's what I'm kind of covering at this point. That's in most current side channel analysis, we actually do need the reference model. And actually, in the next slide, I'm going to talk about what we can do to address this problem.
Right. Thanks.
All right. So this is the challenge with these existing systems, right? That we need a golden chip. But unfortunately, the bigger challenge and kind of like more ambitious and more critical challenge is that there's unfortunately no or very little effort on finding these unknowns, right? I talked about the big hack and talk about similar problems. And unfortunately, in this dialect or chiplet and motherboard level security and privacy, we are facing with this issue that it's very, very difficult to actually know that whether there's something being added that we have no idea that is being added to the system, right? So these two challenges, number one is golden chip, requiring the golden chip, and the second one is unknown unknowns, is what we need to address in our future solutions. And in fact, this is kind of the things that we are trying to do at our research group at UCLA. So essentially, to just give you a very brief overview, these are the ongoing work, so I won't go into the details of each of them, but just to give you a brief overview of each, we are trying to tackle both of these problems that I talked about. Main one is, can we utilize side channels to create a complete golden chip free setting, right? So for example, the main idea there is that can we build a model of the system so that by building the model, we can kind of estimate and predict side channels in order to detect the Harvard Trojans. And the second one is that in the era of dialects and chiplets, can we actually figure out some new models in order to establish the trust on this tiny smaller chiplet. So the first one is, as I said, detecting Harvard Trojan using side channels. And what we did was we started this work of modeling side channels. So essentially there are a very limited number of tools that kind of can predict what the side channel signals will look like given, for example, an RTL code or a netlist. So what we can do ideally is that if we have a better understanding of, for example, given an RTL or given a netlist, can we kind of predict what sort of side channel profile this device might have? We can use this idea in order to actually create a Harvard Trojan model, prediction model, essentially. For example, I'm showing here that we did some measurements with an ARM core, and then we are measuring it for different type of activities in the core. And then we can clearly see the difference, for example, for different activities, for different tool implementation. So the idea is that can we actually use this in order to be reliably, detect Harvard Trojans? And then the second thing is, as I said, is a more ambitious project, which we are trying to see whether we can kind of borrow the ideas that we have at the software level. Like, for example, if you think about the way that we are verifying different software, mainly we rely on this thing called attestation, right? That we kind of compute a hash and then use this hash in order to verify that this software is not compromised. So the idea is that can we actually find a new protocols at the physical level, at the hardware level, that kind of go through different chips, different firmwares, and kind of do the almost similar things that we do at the software level. So the idea is that borrowing some of these established techniques that we have at the software level and then go and implement them at the software level, so that we have, when we're surrounded by these different chiplets, can we actually use them and then go one by one and try to verify. So as I said, if you're interested to know more about this, I'm happy to talk about it offline, but yeah. All right, so that's
the question came in here.
Yeah, go ahead.
Okay, a question, how do you know your golden reference model is trusted, given we are talking about inserting Trojan in RTL, which would involve actual designer of the chips who may or may not be trusted?
Yeah, exactly. So that's I mean, in this scenario, unfortunately, that doesn't work either, right? So, but the challenge in Harvard Trojan really is that most of these Trojans are being introduced during the manufacturing process and manufacturing step, because designing the hardware itself is not as expensive as manufacturing it. So we probably can secure that part by doing the local design. So if you think about the way that works right now, is that most of these systems are being designed, for example, in-house in the US. But when it comes to the manufacturing, we need to outsource this to some other parts of the world. So the assumption here in this specific project is that the designer can be trusted, but the manufacturing foundry cannot be trusted. All right, so that's the end of my presentation. So essentially, to conclude, what I talked about is the Harvard Trojan has been a problem that's been around for a long time, but given the new challenges and the new shift in computation that we are experiencing, we are moving toward more complex SoC systems. More interestingly, we are moving to completely replacing the PCBs and motherboards with this new technologies called heterogeneous systems. So in these scenarios, unfortunately, the Harvard Trojan problem is becoming even more challenging. So we need to kind of revisit the techniques that we have been using for the past 10, 15 years and start thinking about what are other things that we can do in this ecosystem. So this is my contact information. You can also follow me on Twitter if you're interested to know more about this, or if you have ideas that you want to share. I would be more than happy to discuss this with you guys. And thank you again for the time and for listening in.
Great, thank you. One thing that struck me, does this end up kind of being an arms race between the bad guys and people trying to protect electronics? Like you get more sophisticated Trojans that maybe somehow spoof the expected side channel analysis, and even if it's doing something else in there.
Absolutely. And unfortunately, yes. I mean, generally we are in like this whack-a-mole situation right now that like we are trying to like fix some problems and then there is a new attack comes in and so on. But actually, what a fundamental thing that we are trying to do is actually understanding the granularity of detection, like what we can and cannot detect, and kind of like give at least some level of guarantees that, okay, this is the granularity that we can detect things in hardware. So at least kind of like giving this assurance that, okay, at this level we can detect some of these things.
Thanks. Let's see, there's a chat line here. The question here, I thought most Trojans would only run when triggered. How would side channel pick up the dormant Trojan?
Yeah, so I mean, one part of these using side channels for this is actually test generation and creating those situations that the hardware, the Trojan is being activated. So that's like one of the major part of the research, that not only we need to activate the Trojan and then detect the changes, but also we need to find ways of detecting that, activating that Trojan. So the testing and coverage is actually one of the key challenges in this line of research as well. You're absolutely right.
So the testing would include mechanisms to try to activate
Exactly. Yeah. But generally, as I said, the fundamental question that we are trying to answer is, for example, what sort of Trojans we can and cannot detect, right? So there are actually two parts, two phases, right? The first phase is assuming that the Trojan can be activated, can be detected or not. The second question is that given a chip, can we somehow find a way to activate that Trojan, right? So both of them are very important questions. And I think the first one is kind of like more of like a fundamental analysis of the side channels. The second one is more of like, more of like a coverage or test generation problem that we can find, effective ways for creating, this sort of inputs.
And is there some like master library of types of Trojans that researchers keep adding to as they come across things?
I mean, that's a great question. There has been a recent effort. So there is this thing called Trust Hub. There's this website called Trust Hub that's been done by my colleagues at University of Florida. So they actually they put lots of different types of Harvard Trojans there, and it's actually very, very useful set of libraries for that. Yes.
I guess you know better than how to look for things if you know more about what you might be looking for.
Right. So a quick question on the side channel analysis. Does this depend upon always, let's say, when you're looking at, let's say, a microprocessor having a known state, i.e., with something that's multi-threading, you don't know exactly what it's doing at exact time. So if you have two units, you don't know that they're completely in sync. So does the side channel analysis require, having deterministic code running?
Well, I mean, for the Trojan detection, you can, control the environment as well, right? You can control. You're not doing it online. For example, it's not something like malware detection that you like as the execution goes through, you're trying to detect the anomalies. For the Harvard Trojan, you can actually create, a test set. You can run them one by one. You know exactly what should be expected and so on, and then use that in order to detect the Harvard Trojan. So the problem is slightly different than, for example, antivirus detection or malware detection, where you kind of have no idea that what sort of inputs is being generated and being given to the system. Here you have a little bit more control over the system.
Thank you. And once again, I would like to thank our sponsors, Omcore Technology and Advantest, who made these presentations and this workshop possible. So thank you, Omcore and Advantest. Omcore has multiple differentiators as a leading OSAT in areas of technology, quality, and services. And Advantest is voted the best ATE company in 2020 based upon the VLSI research rankings with high rankings in multiple categories. So congratulations to Advantest. So I would like to thank them as sponsors. And I would like to once again thank you for attending and look forward to seeing everybody here again tomorrow, and have a good rest of your day. Thank you.